Okay, guys, I'm Pete from ScoopX, and I want to talk about normal mapping. Well, so what is normal mapping? Normal mapping is basically referred also as bump mapping, but it is different to the bump mapping we used in the demo scene. For example, those 2D bump mapping stuff. Because there we just use some offset for the texture lookups, and when we're using normal mapping, we do a per pixel lighting, and instead of using the normal from the object, we just look it up from a map. Well, this is simple. Just to remember how you would do a per pixel lighting calculation, a Phong model. You calculate the reflection, you calculate the specularity out of the reflection dot product with the viewing vector, and you calculate the diffuse factor by just using a dot product from the light direction and the normal, and then you put that together, multiplying with the color of the texture map with the color of the light, with the specularity color, and then at the end you add the ambient color. So this formula stays the same. The only thing different when using normal mapping is you don't take the normal from the object, you just take it and look it up from a map. Well, it's not that easy, because when normally you store the normals in object space, and if you store the normals in the normal map in object space, you can not really reuse the map. So it highly depends on the model. And I mean the big advantage is that the shader is very simple. You don't need to interpolate the normal, and the vertex buffer gets smaller. But the main disadvantage is that the normal map in object space has to fit to the model. And it's also not easy to do animations, because think about it, if you have a hand and the normal points up, and I move the hand, I want the normal to point in that direction, and it would still point up. So, I mean, you could pass the animation matrix into the pixel shader and do a matrix multiplication per pixel, but that's useless. So what the people do is, instead of using object space, they use the normal map in tangent space, which is kind of relative. So what is tangent space? As I said, it's relative to the object position. What you do is you take the UV information and transform that UV information into 3D space. So you create a matrix out of 3 vectors. The one vector is the normal from the object. The second vector is called the tangent, which is basically the U direction in 3D space, and the binormal is the V direction in 3D space. Well, this is how you would calculate that. I don't want to go into detail here. You can download the slides and the video, and you can also derive it by hand if you want. So, how do you create the normal maps? Well, there are several methods. One nice method I've seen in the net was that a guy just did pictures from real objects. He did from the front, and 3 pictures, one with the light coming from the left, one from above, and one from the top. And then he converted those pictures to grayscale and moved the one with the light from the left into the red channel, the one from above into the green channel, and the one from top in the blue channel. Well, I'm not sure if this is really practical, especially for big objects, houses or so. Another method is, there are people, they say they just paint them. I'm not sure if this is really accurate. Nowadays there are also special programs like ZBrush, where you can easily paint and create really high detail objects, and ZBrush has an option to directly export a normal map. But the most common technology what people are using is they create a high poly model and a low poly model in parallel, and then just calculate the normal map from the high poly model onto the low poly model. There are several tools doing this. For example, the ATI normal mapper. This is the one I'm using, because you can download the source code and look how they do it and patch some things. There's the NVIDIA Melody and also the Crytex Polybump, and I'm sure there are even more. So the main topic of normal mapping, what I want to give you is, when I started with normal mapping, I thought it's just working out of the box. You can download normal map shader, render monkey, and it should work. But the problems are in detail, because the tangent space highly depends on the UV set definition. Then there is a question, what happens if the normals are not smooth, or the tangents? This will produce some seams in the normal map. Then what happens on texture seams, and what about texture compression? Because we're using the normal map as a texture, and if you want to DXT1 compress them, we get some really bad artifacts. Okay, first the UV set definition. Well, you must not do any overlapping things, because what should the tool do if you use the same parts? The tool calculates looks up the normal into the high poly model, and then it has to map it on the same things. This won't work. So you cannot do any overlapping, you cannot do any reusing in the UV set like you would do in the color maps. Then it's really important to do the UV set as linear as possible, to not get some distortion artifacts out of it. You won't see that for color maps, but you will see that in using the normal map. And don't do any degeneration or small faces. For example, if you have a really flat triangle and very high, then the tangent calculation has some precision problems, or might have. So this shows an example when I used hard normals. With hard normals, I mean just flat, what you would do when you flat shaded it. So I have a normal per triangle, and although in theory it should work, and it would work if I would use an older engine or a software engine, but with nowadays hardware there are some problems because of sub-pixel precision and filtering. You get those artifacts here, and it's not practicable to use hard normals. So the conclusion is, use a model with soft normals everywhere, and do all the hard edges in the normal map. Okay, well, and the same you have to do with the tangent and the binormals. So the formula I showed you before was the calculation of the tangent and the binormal per face. And what you do is basically the same what you would do for the normals. You just add them together if they share a vertex, and then normalize it. And yeah, this should give better results. And yeah. Another problem are texture seams. When you, it's not possible most of the time it's not possible to map a 2D-dimensional texture without any seam onto a closed 3D object. So what are you going to do with that seam? And you will see that seam in the normal map. Well, the easiest solution, or its kind of workaround, is you just do it on the same position where there would be a seam in reality. For example, on a trouser you have seams, and yeah, there it doesn't matter. Second workaround could be that you make the seam in theory in between a triangle or a face, so that you can guarantee that the tangents and the binomals stay the same, and that will prevent artifacts from the interpolation. But the real solution is to smooth the tangents and the binomals, even if the UV coordinate is not the same. Well, this has a big disadvantage. I mean, you have to keep an eye on when to move the tangents, because, for example, if you want to reuse some parts, as I said, you should not, but in theory you could. For example, if you have a completely mirrored face, you can just reuse the normal map from the left side to the right, but exactly at the point where you mirror it, the tangents and the binomals look at the opposite direction, and if you would smooth them out, they would result in a zero. So the rule would be smooth the tangents and the binomals when they share a vertex with the same position in 3D space, with the same normal, and don't care about the other attributes like UV or whatever you have, and then check if they are not smoothing them out together. I do that with a simple dot product and with a threshold value, and a good threshold value is about minus 0.8. So if it would have been -1, it would perfectly zero them out, and minus 0.8 is a good threshold. Well, that's good, but when I tested normal maps and I played around with it a bit, and I thought, yeah, it looks nice, but then I came. It has had some strange artifacts, and sometimes I wasn't sure. It seemed like the light was coming from the wrong direction sometimes. So I came out with a kind of list to prove that I can work with normal mapping. And the first thing which really helped was I wrote a small application which rendered the low poly model with a normal map next to the high poly model, and then I could move the light around in the camera, and I saw that the lightning completely fits to the low poly model. Well, this was the first test. A second test would be to check if your tangent and binomial calculation is correct. I did that by creating a normal map from a flat plane and just put some bumps into the high detail map, and then create a simple cube and put the normal map from the plane on each side of the cube, so I have all the rotations, and I see that the calculation in the tangent space works correctly. And as I use the same test application, I had to also make a high poly cube by just copying the high poly bump plane 6 times and make a cube. Well, and a third example, third proof was to flatten out the geometry. This makes no sense in real life, but it shows how accurate your normal mapping routine is. So what we did here was we used a kind of high poly model with some bumps. Then we created a normal map with a flat plane so that the normal map just flattens out the bumps from the plane with the bumps. And well, when you render it, although you have the bumps in the geometry, the normal map should flatten it out completely. And one result was that with ZBrush normal maps, this is not possible. So you don't have the accuracy with ZBrush. And with the ATI tool, this works perfectly. And yeah, last but not least, you can get some problems if you mirror the geometry. If you mirror geometry in, for example, Maya or Max, you have the problem that the normal points into the wrong direction. So you have to adjust the normal, and this could also mess up the tangent space calculation. So the last thing I want to talk is compression, because nowadays it is very important to do compression, because if you do compression, the texture gets smaller, you have more cache hits, and this really pays off. But as I said, DXT1 compression is not a good idea for normal maps, because the way a DXT1 compression works, you get some artifacts, but you don't really see them in color maps, or they are not that big. But you will see really strange artifacts when using this texture as a normal map. So ATI invented their own compression, and what they do basically is they just store 2 components, and the third component can be recalculated in the shader, because you know the normals should be smooth, should be normalized to 1. So you can just multiply and add them together and do a square root to get to the third component. And yeah, the big disadvantage is that this only works on the latest generation of hardware. And you could use some similar stuff by using DXT5 compression and just ignore the blue and the alpha channel so that they don't mess up the compression, and just take the red and the green component and calculate the third component as you would do with the ATI compression method. Yeah, at the end I want to just show some things I have from the web. This is from ATI, where you see on the left without normal mapping and on the right with. So the whole thing here is just in the normal map. And there is a second example which shows it, I think, exactly at the point. This is the high poly model, and here's the low poly model. The high poly model has about 14,000 vertices, and the low poly has 144. And of course you see the hard edges here because of the low vertices, but if you look in the model, it really looks the same as the high poly model. Okay, any questions? Has anyone, then I have a question. Has anyone yet used normal mapping? Okay. Is anyone going to use it? Okay, fine.
Well, okay, then thank you very much. Give him a hand.